2019 paper for Cape Mathematics Unit 2. So let's get into it. All right, so this is module 1, question 1, and it says let 4x squared plus 3xy squared plus 7x plus 3y equals 0. Show that dy by dx is this. So let's go ahead and differentiate this function. So to differentiate this function, of course, we're going to have to use implicit differentiation. When we differentiate 4x squared, what we're going to get is 8x plus 3xy is product, so we have to use product rule. So we keep the first, which is 3x, multiplied by the derivative of the second. When we differentiate y squared, we get 2y times dy by dx, which is y prime, plus we keep the second, which is y squared, times the derivative of the first. The derivative of 3x is 3. Plus, when you differentiate 7x, you get 7. Plus, when you differentiate 3y, you get 3 dy by dx, or you can call it y prime. And now that is equal to 0. Before you even do this step, make sure you told them that you are differentiating both sides. Differentiate both sides with respect to x. With respect to x. All right. It's good that you state to tell them that you are differentiating both sides with respect to x. So now all we need to do now is make y prime the subject. So anything with y prime, we keep on one side. 3 times 2 is 6, and so this can be written as 6x y times y prime plus 3y prime. It's going to be equal to, we are going to bring over the 7 over here, bring over the 8x over here, and bring over the 3y squared over here. So bringing over the 8x, it's equal to minus 8x. Bring over the 3y squared, it is now minus 3y squared. Then bring over the 7 over here, it becomes minus 7. Nice. Now all we need to do is factor out y prime from this expression. So we factor out y prime. Factoring out y prime out from here, all we're left back is y prime from 3y prime is just 3 plus y prime from this 6xy leaves just 6xy. And so y prime times 3 times 6, 3 plus 6xy is equal to, we can factor out the negative from here and write minus of, factoring out the negative, we're left back with 8x plus 3y squared plus 7. This is what we are left with. And so what do we do now? All we can do now is divide through by 3 plus 6x, 3 plus 6xy. And so that means that y prime is equal to minus, in bracket, 8x plus 3y squared plus 7. We divide it by 3 plus 6y, but 3 plus 6y I can factor out a 3. So I can factor out a 3, and I'm left back with 1 plus 2xy. That's how you do this question. Nice and easy, soft. Remember that y prime is dy by dx. All right, so this is shown. Soft, the capital T, soft. Right, so that takes care of question 1, part 1. Now, let's have a look now at question 2, part 2. It says, show that for f of xy, which is equal to 4x squared plus 3xy squared plus 7x plus 3y, show that this is true. I'm going to rewrite what this is saying. This is saying show that 6 times, this is dou f by dou y. I like to write it as the function being differentiated with respect to y. So we need to show that 6fy minus 10 is equal to dou 2f of dou y squared, that is fyy. So I'm just rewriting it in a way that I prefer to see it. fyy times dou 2f of dou y dou x, meaning you differentiate with respect to x first, then with respect to y. So that is f differentiate with respect to x first, fx, then with respect to y, that's fxy, plus, this is now dou 2f of dou x squared. I'm going to rewrite it now, that is just fxx. So this is what we're trying to prove. If this is what we're trying to prove, first we need to do is start with f of x. This is f of x. From f of x, we're going to find the partial derivative of f with respect to x. Differentiating it with respect to x, we get differentiating 4x squared, we get 8x. Then differentiating 3xy squared with respect to x, we get 3y squared. And then differentiating 7x with respect to x, we get plus 7. So that is fx. All right, we're going to need to find fy along the way. So let's find fy right here. Fy would be equal to, this is fy, differentiating with respect to y. When you differentiate 4x squared with respect to y, that's 0. Differentiating 3xy squared, we carry down the power and subtract 1 from the power, so that's 6xy. And then we're differentiating 7x, we get 0. Differentiating 3y, we get plus 3. So that is fy. Okay, we're going to need fyy anyway, so let's find fyy. Fyy means we're differentiating 6xy with respect to y. So this we're going to get 6x. All right, nice. All right, let's also find fyx. Not fyx, fxy. Let's find fxy. Finding fxy means we're differentiating this right here with respect to y. We just get 6y. When you differentiate 8x with respect to y, you get 0. Right? And then it's 3y squared, 6y. Now let's find fxx. So to find fxx, we're differentiating with respect to x, and that just leaves 8. All right, good. So now we need to prove this. Remember, this is what we're trying to prove. This statement right here. This is what we're trying to prove. So first thing I'm going to do is start out with my left-hand side. My left-hand side is equal to 6fy minus 10. So if I have 6fy minus 10 on my left-hand side, let's go ahead and work that out. 6fy, this is fy. 6 times fy is going to be 6 times 6xy, which is 36xy. And then 6 times 3 is 18. Then I subtract 10. So what do I get? I get 36xy plus 8. Nice and easy. So that's what I get, 36xy plus 8. All right, now that I get that, let's go ahead now, moving right along. I now need to show that my right-hand side is going to be the same. So my right-hand side is going to be equal to, my right-hand side is fyy times fxy. Fyy is 6x. And so it is 6x, which is fyy, multiplied by, that is fxy. Fxy is 6y plus fxx, and fxx is 8, so plus 8. All right, now 6x times 6y is 36xy. So this is 36xy plus 8. So I get 36xy plus 8. Nice. Now look at it. These two are the same, so it's proven. All right. Those two are the same, so it's proven. That's how you do that. Nice. Soft. So we justified this. Nice and easy. Moving right along. This question goes to ask us, use the Moivre's theorem to prove that sine 5x is equal to 16 sine to the 5th x minus 20 x cubed plus 5 sine x. So the Moivre's theorem states that, just writing down the theorem, cos theta plus I sine theta. I know that doesn't look like a plus too much, but oh well. Cos theta plus I sine theta raised to the nth power. The Moivre's theorem tells us that this is equal to cos n theta plus I sine n theta. So this is a theorem that we're going to use in order to solve this easy question. Cos theta plus I sine theta to the n is equal to cos n theta plus I sine n theta. So in this case, we're going to let n be equal to 5. If you can give n the value of 5, what you're going to get is cos theta. Well, instead of calling it theta, we're going to use x as well. So what you're going to get is cos x plus I sine x, cos x plus I sine x raised to the 5th power. All of this is now going to be equal to, remember, n is now 5. So since n is now 5, it's going to be equal to cos 5x plus I sine 5x. Yeah, man, that's what we're going to get. You're going to get cos 5x plus I sine 5x. That's what we're going to get. Nice. Now, the part that we really want to show is, we want to show that this 5x, this sine 5x right here, this is the imaginary part. We need to show that the imaginary part of 5x is equal to this expression over here. So in order to do this, we're going to need to expand the left-hand side. So let's go ahead and expand the left-hand side. So the left-hand side, to expand it, we're going to be using, but remember, Pascal triangle to the 5th, it's the first one to the 5th, then to the 4th, then to the 3rd, then to the 2nd, and going down. So this is how we expand to the 5th power again. It's going to be the cosine of 5x. So cos to the 5th power of x plus, then it's going to be 5 times cos to the 4th power of x, and then it is multiplied by I sine x. Yeah, man, you have to remember this, man. Plus times I sine x plus, then it's going to be 10, 1, 5, 10. Then you go down again in power of cos. It's now cos cube. So it's now cos cube x times I sine x square I sine x square plus it is now 10 cos square of x multiplied by I sine x cube plus, then it's going to be 10. So we go 1, 5, 10, 10. So going on back to 5 now. Then it is 5 cos x times I sine x to the 4. And then it is plus I sine x to the 5. I know this is a very big expansion to do. It's very huge. And all of this, remember, all of this right there is equal to cos 5x. All of this is equal to cos 5x plus I sine 5x. Nice. Now this is where you're going to have to know powers of I. You have to know powers of I. You have to know powers of I. So let's get into powers of I. Getting into powers of I right here. Let's get into powers of I. Now, we're trying to prove this I sine 5x, so we need to equate the imaginary part. Now, this is going to be imaginary because we have I sine x right here. Now, I square is minus 1, so that's not imaginary. This part will be imaginary, and this part will be imaginary. So by equating the imaginary parts, we can finally find what sine x is. So let's write that down. Equating imaginary parts. What we're going to be getting now is that this part right here, sine 5x, is equal to 5 cos to the 4 x times I times sine x, because we can ignore the I now because we're dropping off the I, we're equating the imaginary parts. So now sine 5x is equal to 5 cosine to the 4 of x times sine x plus, no, this part where I cube is minus I. So this is going to become minus 10 times cos square sine cube. So it's 10 times cos square x times sine cube x. Nice and easy so far. Then it's going to be this right here, which will have sine 5x. When we have sine 5x, wait, sine x to the 5th rather, sine x to the 5th. So this is plus sine x to the 5th. So sine 5x. Nice. So that is what sine 5x equal to. Now, if you look at the question, you observe that the question had nothing with cosine in it. And so we need nothing with cosine of that sort. So to get rid of cosine, we're going to need to have to substitute for cos something with sine. So let's go ahead and do some substitution. Now, cos to the 4th power is cos square square, but cos square is 1 minus sine square. So we're going to rewrite this as 5 times cos square is 1 minus sine square. So we can rewrite cos to the 4 as 1 minus sine square x. That is for cos square, and this is being squared, and then that is multiplied by sine x. That's multiplied by sine x. Then we'll have plus. When you change up the order, plus the sine to the 5th. Remember, addition is commutative and associative, so it doesn't matter which one I add first. Plus, and right here now, I'm going to change the cos square to 1 minus sine square, so it becomes plus 10 times cos square is 1 minus sine square. So it's 10 times 1 minus sine square x times sine cube x. We're almost finished, man. We're almost. 2 more lines. Nice. So now to expand out 1 minus sine square, that's going to be first term square minus twice the product of the 2 plus second term square. So let's do that. Right? So what we're going to get is sine 5x. The sine 5x is equal to 5 times first term square. 1 square is 1 minus twice the product of the 2, which become minus 2 sine to the 4th of x plus the second term square, and the second term square. And we go again. First term square is 1 minus twice the product of the 2, so it will be, this shouldn't be 4, this should be 2 plus the second term square. Now sine square will give us now sine to the 4 of x. Right? So we get that when we expand the square. And remember, this is now being multiplied by sine x. It's now being multiplied by sine x. We can just put the sine x here. Plus, remember we were adding sine to the 5. We're adding sine to the 5 of x. Plus, we were adding 10 times something. We were adding 10 times this. So we can expand this out to get sine cube times 1 and sine cube times sine square. So it's going to be 10 times sine cube minus sine to the 5th. So this is plus 10 times. Oh, how did I have plus right here? Oh, this was minus. This should have been minus. Why did I change the sign? That should be minus. That should have been a minus here. And so it should be a minus around here. So it's minus 10 times. Minus 10 times. And we said 1 times sine cube is sine cube. It's minus 10 times sine cube of x. And then we said sine square times sine cube. So it becomes minus sine to the 5th of x. Nice and easy so far. Now that we have this so far, all we need to do now is simplify this expression. So let's simplify it. Simplifying this expression, we're going to get that sine 5x is equal to 5 times 1 times sine x is 5 sine x. That part becomes 5 sine x. Then 5 times minus 2 is minus 10 times x is minus 10 sine cube x. Becomes minus 10 sine cube x. Then we have 5 times sine to the 4 times sine x is plus 5 sine to the 5th plus 5 sine to the 5th of x. And then you have plus sine to the 5th. That's plus sine to the 5th of x. Then you have minus 10 times this becomes minus 10 sine cube x we have minus 10 times minus sine to the 5th. That's just plus 10 sine to the 5th plus 10 sine to the 5th of x. All right, and so what we're going to get is sine 5x is going to be equal to sine 5x is going to be equal to sine to the 5th plus 5 sine to the 5th plus another sine to the 5th. That is 16 sine to the 5th. So we get 16 sine 5 to the 5th. And then you have minus 10 sine cube and minus 10 sine cube is minus 20 sine cube x. Then when you have plus what left? Just the 5 sine x. So see, there we prove this question. Nice and easy, soft. There was nothing really to it at all. Nothing at all. Nice. That completes this question. All right, now this question says, write the complex number z, which is equal to minus 1 plus root 3i to the 7th power in the form re to the I theta. So write it in the form re to the I times theta. So let's go ahead and do that. So first, I want to call this piece inside here p. I'm going to call this p. I'm going to call it p to the 7th power. All right, just for now. So the part that is p, I'm saying p is equal to minus 1 plus root 3i. So since p is equal to minus 1 plus root 3i, I first need to think about which quadrant that is in. Minus 1 for x is over here, plus root 3, so it's in the second quadrant. And so the angle is going to be pi plus. This is the angle between the positive real axis and the, all right, so that's the angle that we're going to want. So we needed to just draw the Argand diagram to see what's happening. And so the modulus of p is going to be equal to minus 1 square plus root 3 square. Root 3 square is just 3, all square rooted. So when I work that out, I'm getting a square root of 4, and the square root of 4 is 2. Now that I get that, now I need to find my angle, which is my argument. And the argument, I'm going to call it theta 1. So my argument theta 1 is going to be equal to tan inverse, or pi plus tan inverse of y over x. So it's pi plus tan inverse of, it's pi plus tan inverse of root 3 over minus 1 is minus root 3. And so you put that in your calculator to find out what's tan inverse of minus root 3. Tan inverse of minus root 3. According to my calculator, I'm getting minus pi by 3. So I get minus pi by 3. And so I really have pi minus pi by 3. And so that's going to be 2 pi by 3. Pi minus pi by 3 is 2 pi by 3. 2 pi by 3. Nice and easy. Now that's theta 1. That's theta 1. But what we need is theta. So the modulus of z now is going to be equal to, remember it's being raised to the 7th power. So it's going to be 2 to the 7th power and 2 to the 7th power is, okay, put in my calculator, 2 to the 7th, that's 128. That's the modulus of z. Really sad I didn't remember that. All right, and then now we need an argument of z, which is theta, and the argument of z is going to be 7 times 2 pi over 3. So it's 7 times 2 pi over 3. 7 times 2 is 14 pi over 3. 14 pi by 3. That's what I get for theta, 14 pi divided by 3. Nice. This is what I get. All right, so this is what I get. So moving right along. It says now, hence prove that this is equal to this. Hence, oh, I didn't even finish this part. We didn't finish, so we needed to say then that the complex number z can be written as, it said to write it in the form r e to the I times theta, so it's 128 e to the 14 pi by 3, 14 pi by 3i. All right, because I saw the hints, made me realize that we didn't finish it. So now we finish it, we can continue. And it says, prove that this now. So since it says hence, it means we have to use what we did around there. So the hence, remember we said that z is now 128. Z is now 128 e to the 14 pi by 3 times I. Since it says hence, this is what we're going to use. I don't like to work in exponential, so I convert it to polar form. In polar form, this would be 128 times cos 14 pi by 3 cos 14 pi over 3 cos 14 pi over 3 plus I sine 14 pi over 3. Plus I sine 14 pi over 3. Nice and easy, soft. So now that we have this now we can continue and work out z. You put in a calculator what is cos of 14 pi, you're going to get 128 times the cos 14 pi divided by 3, and you find the cos of that. I'm getting negative a half. I'm getting minus a half right here. Minus a half plus, you find out what is now the sine of 14 pi by 3. 14 pi divided by 3. The sine of that is root 3 over 2. So I get root 3 over 2 times I. Now look what I'm going to do right here now. Instead of writing 128, I'm going to break up 128 as 64 times, 128 can be written as 64 times 2, and then the 2 is going to be multiplied by minus half plus root 2 over 2 times I. Root 2 over 2 times I. And so now we can finish off this question very, very, very easy. This question get too easy now. So what we get is 2 times minus 1 is 2 times minus half. That's just minus 1. So we get 64 times minus 1. And then 2 times root 2 over 2. The 2's cancel, so you just get, oh, this is root 3 over 2. Why did I write root 2 over 2? This should have been root 3 over 2. Root 3 over 2. My apologies there. Check it in a calculator, you get 0.866, which is root 3 over 2, root 3 over 2. And then you finally work this out now. Then you get this 2 cancels this 2, you get plus root 3 times I. Nice and easy, solved. This concludes this question. Proven. Nice and easy. So all of this is now proven. Nice. Now we reach around here. Question 2, it says, so question 1 pretty much dealt with differentiation and complex numbers. This is going to deal with more integration. So it says, let fn of x be equal to the integral of ln x to the n. Show that fnx is equal to x times ln x to the n minus n times fn minus 1 of x. All right, so we're supposed to show this. Now let's do this question now. Show that fnx is this. Now, to do this question, very easy to do this question. So we're going to have to use integration by parts. But first, we're going to have to rewrite fnx. We're going to have to rewrite fnx as the integral of, instead of saying ln x to the n, we're going to write ln x to the n times 1. So it's ln x to the n multiplied by 1 dx. And you might say, what's the importance of 1? The importance of multiplying it by 1, this will allow us to utilize by parts. And by parts tell us that the integral of u dv is equal to what? It's equal to uv minus v du. Yes, this, we have to remember that. We have to. So applying this, we need to call u ln x to the n. So u is equal to ln x raised to the nth power. And if this is u, then you need to find du. What's going to be du? Du is going to be, you carry down the power of n, you subtract 1 from the power to get ln x to the n minus 1. Then you multiply it by the derivative of what's inside the bracket, and the derivative of ln x is 1 over x. So we can just put all of this over x. We're going to then call dv1, and if dv is equal to 1, then v is going to be equal to the integral of 1, and the integral of 1 is x. Nice. Now, once we have that now, what we're going to get is fnx is equal to, using the by parts formula, remember we said in the by parts formula it's u times v, so it's going to be x times ln x to the n, it's u times v minus the integral of v du. Now v times du, if you look at it, you're going to get v times du is going to be x times all of this would become nx ln x to the n minus 1 over x. Now, as you can realize right here, the x's are going to cancel, and you can then factor out the n. You can factor out this n. Let's factor out the n and put the n out here. And so now what you're left back with now is the integral of ln x to the n minus 1. But the integral of ln x to the n is fn. So this is just fn minus 1. So this works out to be x ln x. This works out to be x ln x to to the n minus n times fn minus 1. Fn minus 1 of x. Nice and easy, soft. That's how we do this question. Very easy. All right, nice. All right, so let's go ahead now. And it says, hence or otherwise show that f32 minus f31 is this. Now to do this proof, let's write down, it says hence, meaning we're going to utilize this knowledge. We're going to use the fact that fnx, we're going to use the fact that fnx is equal to x ln x, it's x ln x to the n minus n times fn minus 1. So we're going to use this knowledge. That's what hence mean. Hence mean use this knowledge that you just showed around there to prove this question above. Hence. Otherwise mean you can do something else. But we're going to go hence. All right, so we're using this knowledge around here. Why did it skip do that? All right, so let's use that knowledge that we have. Using that knowledge that we have, we're going to plug in n as 3. N is now 3, so plugging in n as 3, you're going to get that f3 of x is equal to, replacing n with 3, you're going to get that it is equal to x ln x raised to the third power, because you're substituting n as 3, minus n is now 3, put in n as 3, you get f2x, that is f2 of x. Right. Now that that is what we get, we can continue, and so f3x is equal to x ln x cube, it's x ln x, x ln x cube minus 3 times f2x, but f2x is now, to find f2x, we're going to have to go back to this formula again and put n as 2. Put in n as 2, we're going to get x ln x square, x ln x square, minus, putting in n as 2, you get 2 times f, then n as 2 here is 2 minus 1 is 1, so it's 2 f1x. Nice. So this is what we get. You may proceed and go further to expand, and you're going to get x ln x cube. We're going to go x ln x cube. Then you expand in the minus 3 here, you're getting minus 3x ln x square minus 3x ln x square, and then minus 3 times minus 2 give plus, that become plus 6 f1x. So I know the question you're going to ask, we're going to need to find f1x again, sir? Yes, we're going to need to find f1x. Finding f1x, we're just going to replace n with 1. So finally, or penultimately, we're going to get that ln x cube minus 3x times ln x square plus 6f1 is going to be 6 times f1x. Now is we're putting in n as 1, putting in n as 1, we're getting, putting in n as 1 right here, f1x is x ln x to the 1, so it's now x times ln x to the 1, we don't need to do that, minus n as 1, So that's just 1 times f naught. So 1 minus 1 is f naught, so it's minus f naught. But now you're going to ask, sir, how you find f naught? Because if I put in n as 0, you're going to have 0 minus 1. Now, once you reach f naught, go back to the original function. If you were to put n as 0, what would you get? ln x to the 0 is 1. The integral of 1 is x. And so all you have to do now is replace f naught with just x. So f naught is equal to x. Let's do that one more time. To find f naught, you'd put n as 0. If you change n as 0, you get ln x to the 0. Anything to the 0 is 1. And so the integral of 1 is x. So this is just x. So now we have f3x. This is the formula for f3x. Now that we have the formula for f3x, we can find f32 and subtract f31. So now f32 minus f31 is going to be equal to f32 minus f31 is equal to, let's make it have some more space. We're going to go out a little bit. f32 minus f31. f32 mean we're plugging in x as 2 now. So it's going to be 2 ln x, and it is ln x being cubed, 2 ln x cubed minus, put x as 2, you get 6 ln x squared. Then you put x as 2 again, you get plus 6 times, you put x as 2 here, 6 times 2 is 12, so this is really plus 12 ln x. So erase that and put plus 12 ln x. Then you put x as 2 here, you get 6 times 2, that's minus 12. You close up that bracket, and then you subtract. What you're going to subtract is f3 of 1. So you put x as 1 is in here. When you put x as 1, ln 1 is 0. So you're just going to get 0 minus 0 plus, putting in x as 1 here, you're going to get ln 0. ln 1 is 0. Put x as 1 here, you get minus 6. So that part becomes minus 6 in here. So this part becomes minus 6. And so now you may proceed and go ahead. And you're going to have all of this, but minus 12 minus minus 6 is just minus 6. So all of this works out to just be 2 ln x cubed minus 6 ln x squared minus 6 ln x squared plus 12 ln x minus 6. So proving this question nice and easy, soft, a capital T, nice. This is proven. All right, moving right along. Moving right along, it says, by expressing y squared plus 2y plus y to the 4 plus 2y squared plus 1 in partial fraction, show that this is true. So let's go ahead and do this question by expressing it in partial fraction. So I'm going to call this I. Don't like to write out this whole heap, so I'm going to call it I. Calling this I am getting that I can write that I is equal to y to the 4 plus 2y squared plus 1. I can then be equal to ay plus b over all of this right here is really y to the 4. All of this can be broken down. What I'm saying is that denominator, y to the 4 plus 2y squared plus 1. This denominator right here, if you really examine it, you're going to see that this denominator is really just y squared plus 1 being squared. That's all it is, y squared plus 1 being squared. So when you're separating it as a partial fraction, you can rewrite it as ay plus b over y squared plus 1 plus cy plus d over y squared plus 1 all squared. That's how you separate it in partial fraction. Nice and easy. So there's no issue with this question. This is how you'd separate it in partial fraction. Nice. All right, so let's go ahead and continue. So continuing this now, all we need to do is express this as one fraction first by finding the common LCM, which we know is y squared plus 1 all squared. And so this into this just leaves y squared plus 1. So it's going to be ay plus b and this is multiplied by y squared plus 1 plus y squared plus 1 all squared into y squared plus 1 all squared is just cy plus d. That's what we have. Nice. So let's go ahead now. Keep on working, keep on working. So you have to have ay plus b times y squared plus 1. Ay times y squared is ay cubed. Then ay times 1 is ay. And then b times y squared is by squared. And b times 1 is b. Plus cy plus d. Nice and easy, soft. And then now you have right here, you have y squared plus 2y plus 1. Remember, that's what I is, y squared plus 2y plus 1. And that's by equating the numerators. Let me move over this equal sign. And their denominators are the same, so we don't even need to look. We can just ignore the denominator now. We can just ignore the denominator because the denominator is both the same. It's both y squared plus 1 all squared. So when the denominators are the same, we're equating the numerators. So that's what we're going to do now. So right here, we're equating numerators. So equating the numerators, what do we notice? We notice there's no y cubed over here. And so clearly, a is equal to 0. If a is equal to 0, then what do we know? If a is equal to 0, then equate the y terms, the y squared terms. Equating the y squared terms, we're going to get b equal 1, clearly. Then equating the y terms, we're going to see that 2y is equal to ay plus cy. And if 2y is equal to ay plus cy, then if we divide through by y, we get 2 is equal to a plus c. But what do we know? We know that a equals 0. So that's telling us that c equals 2. And then if c equal to, equating our constants, we have b plus d is equal to 1. Equating constants, 1 is equal to b plus d. And since 1 is equal to b plus d, but b is 1, then d must be 0. So d is equal to 0. Now that d is equal to 0, we're good. So ay plus b is going to be ay plus b. A is 0. So 0 times y is 0 plus b. B is 1. So it's now 1 over y squared plus 1 plus cy. C times y is 2 times y, which is 2y, plus d. D is 0, so it's just 2y over y squared plus 1 all squared. So there you have it, nice and easy, soft. So we've shown that this partial fraction is true. That's what we get when we separate it in partial fraction. So proven, soft, giving away 7 marks. All right. Now, hence, calculate the integral of this. Now, when it says hence, it means you're going to use the partial fraction to do it. So I like to call this integral I. So I'm going to say I is now equal to, we're using what we just found. I is now the integral of 1 over y squared plus 1 dy plus the integral of, what was the other piece we got? 2y over y squared plus 1 all squared. That was the other piece we had gotten, dy. So if this is what we're going to be evaluating, then we can proceed. We may proceed to work this out now. We may proceed, and the integral of 1 over y squared plus 1, that's just tan inverse of y. You have to know those by heart. This is just tan inverse of y. That's integration by recognition. Plus, now this part now, to do the integral of this part, what you're going to have to do is do some substitution. I want you to call u y squared plus 1. If u is equal to y squared plus 1, then what is du? Du is going to be equal to 2y dy. So what does that mean for us? That means that this piece right here is going to become the integral of, use the u substitution, it becomes 1 over u squared du. And so what we're getting is that I is equal to tan inverse of y plus, now when you're integrating 1 over u squared, that is u to the minus 1. And so you can write it as minus 1 over u. That's what you get when you integrate 1 over u squared. Then remember, when you integrate, you put plus c. But then what was u? U was y squared plus 1. This is just tan inverse of y. Tan inverse of y minus 1 over u, which is minus 1 over y squared plus 1. Plus some constant c. Nice and easy, soft. Nice. That's how we do it. Nice and easy. Moving right along. Oh, we finished.